C5 Chemical Changes Test Foundation. Okay, question 1. Questions about acids and bases. We put a box around the command words so we know how to answer the question. This is asking us which, so identify which ion. And then underline key information. Okay, so we'll do that for all the questions. In this case, the ion that acids produce is H+. So anything that produces H+ ions when it dissolves in water is an acid. And the opposite is OH-, which is an alkali. Part B, zinc nitrate can be produced by reacting an acid with a metal oxide. So here we are going to name the acid and the metal oxide to produce zinc nitrate. Okay, so we break this salt name down, zinc and nitrate. The second part of the salt name always comes from the acid. The first part always comes from the alkali. Okay, so the acid that produces nitrate is nitric acid. And the metal oxide must be zinc, okay, to give us zinc oxide. Okay, what does AQ mean in brackets here? It's one of our state symbols. It's used in equations a lot. It means it's dissolved in water, or aqueous, okay, which is where the AQ comes from. And part D, if we have a solution which has a pH of 8, we add acid to it, that pH is going to go down, so the number is going to get smaller. So any number from 7 down to 1 or even 0. Okay, so any of those numbers will be fine. Part E, we're looking at the solubility of 3 solids in water at room temperature. The first table of information shows us how well they dissolve. So phosphorus oxide dissolves quite well. Silicon dioxide doesn't dissolve at all. Sodium hydroxide dissolves really well. Second table of information shows us that solid A produces colourless solution and has a very high pH, which means it must be a strong alkali. B is a colourless solution and has a pH of 2, which means it's a strong acid. And C doesn't dissolve, has a pH of 7, which means it's neutral. Okay, so all that information is there in the table. They're asking us to describe a method that could be used to identify each of the solids A, B, and C. And the second part of that question stresses you must use an indicator. Okay, so I've broken this down into 5 steps. Let's just move the camera out a little bit so we can see. So step number 1, add the same volume of water to each solid, so 100 centimeters cubed. Step 2, add the same mass of each solid, for example, 5 grams. Step 3, stir for 2 minutes until no more solid dissolves. Step 4, add universal indicator. Goes back to this part here. Step 5, use the colour chart to measure the pH of the solution. So the universal indicator will change colour and the colour will give us a value of pH. Okay, there are 4 marks for that and I've given you 5 possible pieces of information you could have used. Okay, use the table of information to answer these questions. So we've got an acid here, produces H+ ions, low pH. Sodium hydroxide is an alkali, produces OH- ions and has a high pH. So we've just got to circle the correct answers. Sodium hydroxide is alkaline because it contains OH- ions. Coming back to this, okay? pH of acids is lower than the pH of alkalis, okay? So that's also in the table. So all that information is there, you just need to find it. Okay, so we're looking at this experiment here, which you may not have come across. We'll have to have a look at this when we get back. This is a titration, and we're adding an acid here through this tube, it's got a little tap on it, into this conical flask containing sodium hydroxide solution. All right, you can measure how much acid you add by these graduations. This is called a burette. So first part, nice and easy. What is this piece of equipment here? Well, it's a conical flask. Part 2, the method used is titration. Okay, we'll have a look at this in a bit more detail. You don't need a lot, you just need to know what it is. Suggest one way to make the results more reliable. Repeat the experiment, calculate the mean. Stock answer. Okay, so if ever you get a question about reliability, you talk about repeating the experiment and calculate a mean. Part C, describe. So box the command word. So we're saying how we're going to do this. How an indicator can be used to show when all the sodium hydroxide has reacted with sulfuric acid. So the indicator will be a particular color when it is in the alkali. So for example, pink. There's a particular indicator called phenolphthalein, which we use quite a bit, and that is pink in alkali. When the alkali is neutralized by the acid, the indicator changes color. In fact, it becomes colorless. Okay, so we know when all of the alkali has been reacted because the solution changes color, the indicator changes color. So that's the whole point of adding the indicator. Okay, question 3. Solution of Y was slowly added to a solution of X. The graph shows how the pH of the resulting solution changed. What was the pH of solution X? So we box the command and we underline the key information. So solution X is going to be the pH at this point here before we've added any alkali, which is the Y. Okay. As we add Y, the pH changes. So here it's just below the 3. So if we zoom in on that one, we can see it's just below the 3. All right. So we'll accept answers between 3 and 2.7. State whether solution Y was acidic or alkaline or neutral. Well, we know it's going to be alkaline because as we add Y, the pH goes up, it increases, which means it's becoming more alkaline. What volume of solution Y is needed to react with all of the substance in solution? Well, this is 25 centimeters cubed, and you can find that on your graph. If you look here, it's the point at which the graph changes vertically really quickly, okay, which is 25 centimeters cubed. And it's the only number on the graph, so it makes it even easier. Okay, last bit. Chemical equation shows the reaction between an acid and an alkali to form a salt and water. Draw a circle around the formula of the alkali. The alkali always has OH or just O or CO3. So it could be an oxide or it could be a carbonate in there. They're your 3 options, okay? So OH, O or CO3 at the end is going to be an alkali. And your acid always has the hydrogen in there, okay? What is the formula of the salt? It's K2SO4, which is given there, okay? So salt and water. Acid plus alkali always gives us salt and water. Okay, question 4. Student plans a method, does a really bad job of it, and they ask you to come up with an explanation of how it could be improved. Okay, so explain is our command word. We're looking at improvements, and we want pure crystals of copper sulfate. Okay, and that's really important. The copper sulfate part is really important because what they've added is calcium carbonate and hydrochloric acid. So what will that make if we react them together? It will make calcium chloride. Okay, that is not what we want. We want copper sulfate. So we need to change the reagents to start with, but we're going to be more specific as well. So we're going to add 10 centimeters cubed of sulfuric acid to a beaker. This reacts to form the sulfate that we need. Okay, this bit. Don't worry about the spelling. Okay, I'm a bit old school. The spelling with the F is American, which is used more now. Part 2, add copper carbonate until there is no more fizzing. So we're adding copper carbonate instead of calcium carbonate because we want copper sulfate crystals. Okay. Until there is no more fizzing is important because we want the reaction to be completed. We don't want any acid remaining in that beaker. This is the reaction. Put the equation in where you can. If you can't do the simple equation, do word. Okay. So copper carbonate plus sulfuric acid gives us copper sulfate, water, and carbon dioxide, which is where the fizzing comes from. This gas is released. We're then going to filter it because what we've done, we've reacted all the acid and there'll be some copper carbonate left over. So we want to get rid of that. So we filter it. Then we pour the filtrate into an evaporating basin. And the last step, we warm it until all the water is evaporated. So you could use a Bunsen burner or you could use a water bath, which is just boiling water in a pan basically, and your evaporating basin sits over that and the water evaporates off. There are 6 marks to this. Okay, so the key things you need to know are we're changing the acid, we're changing the carbonate. We're adding specific amounts of each, put an equation in, word or symbol, and then we talk about filtering the mixture to get rid of that. Pour into an evaporating basin and we evaporate it off. Okay, so there's loads of specific marks within that you can choose from. Last part here. Zinc is extracted by removing oxygen from zinc oxide. What is the name given for a reaction in which oxygen is removed from a substance? It's reduction. And you remember the opposite of reduction is oxidation. Oxidation is where it gains oxygen. Reduction is where something loses oxygen. Okay? So in this case, the zinc loses the oxygen, so it is reduced. Okay. Acids react with alkalis to form salts and water. Complete the table below. This is relatively straightforward. If we look at nitric acid and sodium hydroxide, the acid part, the nitric, sulfuric here, will give us the second part of the salt. So nitric gives us nitrate. The beginning of the alkali, sodium or potassium, will give us the start of the salt. So sodium here. So this is sodium nitrate. And that's the formula, NaNO3, sodium nitrate. Here we've got potassium sulfate, okay, and K2SO4. You may not have realized that this has to be a 2 in here, okay? And that goes back to the bonding work we did in C3. They give a reactivity series here and ask you to place carbon in there after giving you some information. So they tell you that carbon's used in blast furnaces to obtain iron and zinc from their oxides, but electrolysis to obtain aluminium from its oxide. So we know from that information that carbon must be between aluminium and zinc. So we show that on the series, okay? So that now they're asking us to predict a method of extraction to obtain calcium from its ore and explain your answer. Okay, so the prediction is electrolysis. How do we know that? It's because carbon is less reactive than calcium. So it can't push it out or displace it from its compounds. Okay. Part C. The formula for zinc oxide is ZNO. Write a balanced equation for the extraction of zinc in the blast furnace. So what are we going to do? We're going to add zinc oxide and carbon. We're going to react them together at high temperature. The carbon takes the oxygen away and it leaves us with just zinc. And to balance that out, because we've got CO2 here, we've got 2 oxygens. On this side, we've only got 1, so we need to double it. Which means we've now got 2 zinc here, so we add 2 here to balance that. Okay, and that is the end of the test.